So we're now ready to do some predictive modeling, and in this situation we're going to be trying to predict whether or not at the time of an error message being generated, at the time of a task being raised for the organization, for the field force, and whether or not that job will result in a part needing replacing. And to refresh your memory of what the data looks like, it's just browse it again. Of course, we have the structured data that we saw earlier on, which is the incident ID, the date of the error, the region that they're in. And we also had some information about the nature of the assets itself. But we also have the error code, which has been used before. And you also see now that we've got some additional fields, which are flag fields, which is the error, a result of the mining the error text. So you can see here it says error cooling, for example, that's flagged as one. And that's coming from this piece of text at the end, which we've mined. You can see it says fault and cooling fan. So that's being mined out and turned into fields. We've done exactly the same thing with the engineer response, where it says replaced cooling unit. So a part replacement has occurred there. And that has allowed us to create these fields where we can see the fix that has occurred. You can see it says fixed cooling, and it'll also have a fixed fault replaced, so part replacement has occurred there. So this is actually going to be our target field, this part replacement, and it's coming from the text. It's not something that's actually contained within the structured information. It would be better if it was contained from the structured information, because we're really relying on the text to tell us if a part replacement occurred, but we can do a pretty good job of estimating the part replacements from the text and whether or not that was a part replacement was required. You can also see it says along the side here, fixed category part replaced. So we can also use that as a way to identify whether or not a part was replaced. To do this, what we're going to do is identify what's called the key field and identify what are our input fields. So if that sounds a bit technical, let me just show you this little type node here. The type node consists of a list of the fields that we could use. And you can see all of these fields here, if the role input can be used by a predictive model. All of the fields of the role none won't be used by the predictive model. It's very important for us to use data which we would have known at the time the error occurred, and not to use information that we couldn't have known at the time the error occurred. So we're very careful not to use anything that has been gathered as a result of the maintenance. The only thing that we're using that's been gathered as a result of the maintenance is whether or not the fix included a part replacement, and that's our target field. If we actually look at this little data audit node now, we can see that it's colored each of these input fields, or each of these potential fields, by whether or not a part replacement has occurred. Here's the part replacement. Gold for yes, a part has been repaired, and green 0 for no, it hasn't been repaired. And we can double click on that and see that as a chart, see what the proportion is. It's about 25% of the time a part has been repaired. We can see information that we've gathered and brought in from environmental factors such as weather here, so we can see maximum temperature of the day, mean temperature, precipitation, rainfall, etc., etc. These may have a bearing on whether or not a part occurred, or whether or not something else has occurred, such as the nature of the fault or the type of part that's been replaced. Okay, so having set that up, how can we predict this outcome? If we look along Modeler's array of techniques that it has to uncover and build models, and there's quite a wide range of them. Now, in fact, this particular problem is called a classification problem, because we're trying to predict whether or not you're in a 1 or a 0 outcome, i.e. whether or not a part has been replaced. And that narrows down the field of algorithms that we can use, or techniques that we can use. But again, it's quite a wide range of them, and one might be, forgiven for thinking that, well, actually this is fairly daunting. And as it turns out, we've got something up our sleeve. We've got what's called an auto classifier, and I've got one set up here and ready to connect to the data. So if I just connect that to the data and explain what we're going to do, you can see immediately it's picked up what the target field is. It says fixed part replacement, so it knows that's the thing it's trying to predict. And what it's going to do is it's going to use all of the relevant classification techniques that it's got from its stable of algorithms to try and predict that outcome. And they're basically going to have a competition where the top 3 are chosen, and then the top 3 are chosen are based upon the accuracy of the model that they produce. So if I want to run that, it starts the process and says, okay, well, I'll try and find the first top 3, and then I'll see if I can improve on it. So you can see it says models retained 3, models discarded 1. It's still got 6 to go, so it's then got, now it's discarded 5. It's finished now at this point, and it produces what's called a nugget for us. And this nugget, a bit similar to what we saw earlier on with the text analytics nugget, but this nugget in this occasion contains 3 predictive models, and we can see inside it, if we click on edit here, we can look inside and see how accurate these models are, and we can see which algorithms it's chosen. It's chosen 2 different versions of the same algorithm called C5, and it's chosen a third one here, which is the Chade algorithm. These are all actually part of the same sort of family of techniques. They're called rule induction or decision tree algorithms. They're very commonly used, and they're very easy to work with because they're very visual. We can see the overall accuracy of the model, which is 84% here for the C5 model. We can see how many fields it's used. And we can see even what the error rate is in that model. So if I double click on that little chart there, I can see that, you know, it's doing a pretty good job of identifying the part replacements, because here are the part replacements. Here's the number of part replacements. It's finding over half of them, I would say, probably about half of the part replacements, and sometimes it's missing some of them, so it's not finding them all, and there's some error in the model. But that's what we would expect. We'd be very alarmed if it was a perfect model. It would almost certainly be a mistake or a problem in our model. So this looks quite good and quite heartening. If I want to look inside the model itself and see how it's done that, then you'll find that the model consists of a series of rules. So I can double click on the nugget here and see that one of the first things it's chosen is it's saying if error transceiver issue is mentioned, so if the error message mentions a transceiver issue, then that generally results in a part replacement, hence mode is equal to 1. If it doesn't mention it, it generally results in the part replacement not occurring. And I can unfold these rules and say, well, if the minimum temperature, you know, is less than 5 degrees, then that's even more likely to occur. But if it's greater than 5 degrees, it also occurs, but there's a slight difference in the frequency of it. Then it starts to look at the site technology, and it says, well, you know, if it's one of these types of technology, Series 1, Series 1A, Series 2, Series 3, Series 3A, then I expect it to be a part replacement. But if it's using Series 4, then no, I don't expect it to be a part replacement. So that's an exception to the rule that it's producing. And if I click on this little percentage button here, it will show me the frequency of occurrences of each of these groups. Perhaps an easier way to view it is as a decision tree. And if I click on viewer here, we can see that the model consists of a hierarchy of factors, and it says, okay, transceiver issue is the most important. 860 part replacements have occurred, and 44 of those have occurred when transceiver has been mentioned, and which is as a proportion, when transceiver error has been mentioned, and that's 77% of the 57 times that transceiver has been mentioned. So it's quite a high lift value there. If it isn't mentioned, then it's a 24% part replacement, which is just slightly less than the baseline of 25%. So we follow this down. We say, well, if the minimum temperature is less than 5, then it always happens. If it's greater than 5, then it jumps to 62% or drops to 62%, and then we can see the difference in whether or not a Series 4 technology is used, and then whether or not the activity is hardware or site related, and so on and so on. So it's going into subgroup of subgroup, subgroup, and the entire model consists of a tree where we start with all the data at the top, and the data flows down through it until eventually we get into very, very small subgroups. And the goal of the model is to try to find rules which describe the difference between a part replacement being required and a part replacement not being required. And we can use that model to build predictions. The Chade model will be very similar, but this time it's focusing on the error codes. So if I look on the error codes, it's starting to group together the error codes that are used. That's one of the reasons why it's able to use its ability to group together all these error codes is one of the reasons why it uses fewer fields. So that's actually a simpler model in some ways. It's just saying, well, you know, these groups of error codes elicit a high degree of part replacement. So here we have 82% versus this group of error codes only 39% versus this one 29%. These error codes never result in a part replacement, and so on and so on. So we can actually we can actually start to see which error codes are most strongly related to a part replacement. So this model's pretty good. I can actually get it to switch off the other ones and say, well, just choose this one model, or I could get it to generate that model and say, okay, go and pull that model out, and I could, you know, put it to one side and test it. So if I want to flow the data down through that and see how accurate it is, one way in which I can see how accurate it is by using what's called an evaluation plot here. And if I hit edit at this point and just change some of the settings in there, click run, it probably makes more sense if I show you the chart. The chart is showing the difference between a perfect model, a random model, and our actual model. So a random model would look like this red line, where we could only find 25% of the part replacements from randomly sampling 25% of the data. If we wanted to find all of the part replacements randomly, we'd have to sample all of the data. If we had a perfect model, we would be able to find 100% of the part replacements from 25% of the data. But using our model, we can find about 58% of the part replacements from 25% of the data. Now, if you wanted to use that model to make predictions against, you know, future events or future incidents, then it's pretty straightforward to do that. All you got to do is pretty much make a copy of it, or use the original one, but I'll just make a copy of it here. So I'll copy and paste it, and I can connect it up to some new data where we don't know the outcome. We don't know if a part replacement is required, and I can just show you that data set by putting a table node up here. This is called scoring the data, making predictions. So you can see we've got an incident ID here, we've got new information, we've got, you know, error messages which are being generated, and that data has already been mined for us. So we've mined it using the text analytics model that we produced earlier on. We've got temperature data which may be relevant to it. Of course, we know that comes up in the model. We've got the error code. At no point do we have a field saying yes, a part replacement is required here, because of course we don't know. We need to get the model to actually predict that for us. So if I show you what the model produces, once having connected it to that data, what we'll see is that the model produces two new fields for us at the end here, and they both have the prefix $C to indicate that they come from a C5 model, and the dollar indicating it's a system variable. And the first prediction here is one, a part replacement is going to be required, and it has a confidence value. It's 93% confident that is going to be required. Here it's only 57% confident. Here it's 83% confident. Zeros are where it thinks a part replacement is not going to be required with their associated confidence value. So to clean that up a little bit and maybe send it on to a workforce management system, what I could do is simply connect a filter node to that, and that allows me to mask out all of the non-relevant fields. So I can just go down here and say, okay, I'm only interested in the prediction itself, whether the part replacement is going to be necessary. So I could say, okay, just show me these three fields that you've got, which is the incident ID and the prediction and the confidence. So here's the prediction, and I could go further and actually say I'm actually only interested in those where, you know, the value is predicted to be 1. So I could say, okay, go and generate a select node for me of that, and it would generate a little what's called select node, which would filter out all of the zeros. So it's saying only show me where it predicts it to be a 1, and that would produce obviously a list of incidents where a part replacement is likely to occur, and here's the associated confidence with that. And of course I could then export that back out to a database, back out to a flat file to be picked up by another system, or back out to Excel, whatever is required at that point. And I could automate the process. So I could build a process so that the entire business of scoring the data, mining the data, producing predictions, masking out the fields, and sending them to a third-party source is automated. And if I'm really clever about it, I might go further and try to estimate the consequence values associated with the part replacement, or try to estimate which parts are going to be replaced, and then, you know, really bring some accuracy and some value to the whole application.